Stephen mentioned there, my name is Barry. I am an engineer with Grant Engineering. So today we are going to, sorry, no, my screen. Sorry, there, 1 second. Sorry there, we just had some technical issues there. So today we're just going to have a brief overview on heat loss, what it entails. So fabric heat loss, ventilation heat loss. We will have a look at heat loss calculation, what's involved, what's required, and then we'll also just have a quick look at DEAP Software, what it is, what it does, and kind of the information that's required and what comes out of it. So just a brief overview of the company I work with. So it is Grant Engineering. Grant was established by Stephen Grant in Burr in 1978. In 1996, Grant UK opened in Devizes, and in 2018, Grant France was established in Chambéry. In addition to these kind of main headquarters, we would export into many different countries around the world: Denmark, Greece, New Zealand, Finland, and so on. We originally would have started off making solid fuel back boilers, which then progressed into oil boilers, which led to the condensing oil boilers, wood pellet boilers, solar panels, heat pumps, and so on. To where we are today is whole house solutions, so heat pumps, cylinders, underfloor heating, radiators, biomass. So we kind of cover a broad range of heating products for the market. Right, so basically, what is heat loss? So in its simplest terms, heat loss is a measure of the total heat transfer through a building from internal to external via either conduction, convection, radiation, or combination of a few of them. Heat flows from hot areas to cold areas. This will be derived from the second law of thermodynamics. So this is it will always flow from hot to cold. Most homes will be maintained in around 20 degrees approximately. The average air temperature externally will be well below this. So this would lead to a change in temperature, which means that you're going to have heat transfer from inside to outside. Heat transfer or heat loss then will be measured in what's called watts, or more commonly kilowatts, and then maybe in the older terminology, BTUs, which would be British thermal units. So the first part of heat loss will be fabric heat loss. So fabric heat loss will be the amount of heat loss through the physical elements of the building, such as the walls, ceiling, floors, windows, etc. The information that is required in order to calculate fabric heat loss is you need to know the internal design temperature. We need to know the external design temperature. We need to know the surface area of the specific element, so maybe the window, the wall, the floor, and then we also need to know the U value of the element. When designing a building or a retrofit from a heating perspective, the element areas themselves are generally set by the homeowner's requirements or by the existing building. So the wall is already built, the window ope is already built. The temperature difference between indoor and outdoor will be set by the climate. So you would have your average changes outside, you would have your design temperatures inside. So the only real value that can be adjusted from a design perspective in heat loss will be the actual U value. So we can increase the insulation, or we can increase the quality of the window, etc. So from a fabric point of view, to minimize the heat loss, we must minimize the U value. To calculate then the fabric heat loss, the simplified calculation can be given as Q is equal to U A delta T. What this means is, so Q, the actual heat loss of that element, is the U value of the element times the surface area of that specific element times the temperature difference between indoor and outdoor. The overall heat loss then of the building fabric would be the sum of the U value of all the different elements and the different temperature changes. The second part then when calculating heat loss is ventilation heat loss. There's two primary causes of this. So we have ventilation and infiltration. So the movement of the heated air within a space, transferring from inside to outside, lost to the surroundings, and then being replenished with cold air. The difference between the two, so ventilation is the deliberate process of replacing air in any space to provide high indoor air quality, whereas infiltration will be the uncontrolled ingress and egress of air into any space through air leakage points. Air infiltration provides a significant amount of heat loss from a building. So in order to reduce this, what we need to do is increase the level of air tightness. The CIBSE Heating Design Guide and what the standards we would use in Ireland, NSAI SR 50-1 and SR 50-4, which will relate to plumbing and heating and heat pumps. So when we are designing heat loss calculations, there is a number of set criteria. These will be internal design temperatures for different rooms. So each room would have a specific target based on comfort levels, which are required to be reached. They would also have then a specified air change rate. So this would be the volume of air that's required to be changed within that room over a certain period. So if you could see here, this is an example table from SR 50-1. So it would have a list of different rooms. So we take, for argument's sake, a living room would have a design temperature at 21 degrees. A new build, then it would need 0.5 air changes. Or if it was an older building, you will be looking at 1.5 air changes. So once we get to the calculations, we'll see the difference this makes. So it can have a very significant difference. These, I suppose, are kind of standard simplistic values. These can be adjusted once we factor in ventilation. So if we had heat recovery ventilation, for argument's sake, the ventilation rates can be, the ventilation heat loss is possibly reduced because we can recover the heat that's been replenished back into the room. But for basic, simple terms, we're just going to keep it at these values. Secondly, then, if there is chimneys or flues or permanent vents or different bits and pieces within rooms, then the ventilation rates would obviously have to be increased to account for these. So the ventilation heat loss, the calculation for this would be 0.33 times V times N times delta T. Q being the heat loss again, 0.33 then would be a combination factor of the density of air and its specific heat capacity. V being the volume of the room, N being the number of specified air changes for that room, and then DT being the temperature difference between indoor and outdoor. So if we combine our previous calculation for fabric loss and then we combine our ventilation loss, that total heat loss can be provided by the sum of the elemental area times the U value plus 0.33 by the volume by the air change, all by the temperature difference between indoor and outdoor. So once we move on to a heat loss calculation, what we need to know or factor in is that if we're taking standard residential premises, each room would have to be treated as separate. This because each room would have a specific set of design criteria. It would have its own design temperature. It would have its own specific air rate. So we need to factor each room as specific, and then we can sum total them then at the end. And then I suppose the most important thing then is that heat transfer will only take place when there is a change in temperature. So there has to be a temperature difference for heat transfer to occur. So when we're doing internal calculations, if there is no change in temperature, so for argument's sake, 2 bedrooms side by side, both designed to 18 degrees, the internal wall between 2 bedrooms will have no temperature change across it, so there'll be no heat transfer taking place here. This also can occur with intermediate floors and anywhere else where it has same temperature on adjacent sides. So there are many different methods of doing heat loss calculations, different procedures and so on. This here is an example from SCAI's website. So SCAI have a sample workbook on their website, which can be downloaded in order to aid people completing heat loss calculations. So this would it came straight from their website, so it's free to download for anyone. So it makes it easy starting off. You can see what's involved. So then factoring in what we've said about the different types, if we start at the top, then you'd have your room specific. So this would be the actual type of room it is, whether it be a kitchen, a bedroom, a bathroom. Then it would have its corresponding design temperature and external design temperature. In Ireland, we generally would take a design external temperature of -3 degrees. We can generally would take this for the whole island. Once you kind of move, if you were doing heat loss calculations in the UK, up in say Scotland, you would possibly use in -7, whereas down south of England, you might be using 0.1 or 0. So the external design temperature generally can change, but for Ireland, we would usually keep it at -3. So it would keep it as a constant. The next section then, if we look at the actual ventilation heat loss, so you can see here, we'd have the number of air changes per hour. So this would have come from the table. So for our specific room, we need 1.5 air changes. Then the next part of that equation was the V, the volume. So we have the length by the width by the height. So with the volume of the room. So the amount of air then to be heated in the room. So this will be your air change multiplied by the volume of the room. And then we will have our air change constant, 0.33. And then our design temperature, or the temperature difference between indoor and outdoor. In this scenario, we have a 21-degree internal, a -3 outside. So the temperature difference being 24. So the ventilation heat loss for that room, we've now calculated at 377 watts. This room has an open flue or a chimney. So because of this, we need to allow for this. So if we, from our SIBSI heating design guide, we can see that the allowance required would be 3 air changes. So if we would plug in the same thing, our additional extra over now is an extra 754 watts just by having that open flue or chimney. So you can see here that the total ventilation losses for this room is it's about 1.1 kilowatts. So it's fairly significant for a room that's only 4.9 meters by 2.7 meters in area. Next, you would move then to the fabric heat loss. So the fabric heat loss then, what we would do is, for simplicity, you would treat every room as a cube. So it has 6 sides effectively for heat transfer. 4 sides around the back and then to top and bottom. Now, whether there's actually heat transfer taking place, that is down to whether the adjacent room has a temperature difference. So if we take here, we have an external floor, we have our area 4.9 by 2.4, which is 13.23 square meters. The U value in this scenario being 0.77 and our temperature difference. So the heat transfer through the floor being 244 watts. We would follow this down along then, and you would fill out all the different elemental areas on the 6 sides or however many sides, but generally we take it as the cube in 6 sides. You have our external wall, so gross area. Then you would have your windows. We'd have our external doors. Then you would get your actual net area, so external wall, so minus any windows or doors to get a true value. You'd have your roof lights. So these are all the same. So you'd have your area times your U value times your temperature difference, which is given the heat loss through each one of the elements. You would carry this on down through all the different elements, and you would get then our sum total for this room being 1,758 watts. So you will complete this then for every room in the house. As we can see, the total for the room being 1,758 watts, but we've already seen that the ventilation side of it is 1.1. So almost 2/3 of the heat loss for that room is lost by ventilation losses. This, I suppose, is probably the most misunderstood part in heat loss, because if you were speaking to anyone that's out designing a heating system or installing, everyone can imagine the window has a specific U value or the wall is well insulated. So they can have some bit of a grasp on the fabric heat loss side of things. But the actual, when it really gets down to the nuts and bolts of it, the ventilation is probably as important, if not more important, as the fabric. So this would mean that in order to reduce this, we need to reduce the air, or we need to increase the air tightness in order so that we can reduce the air changes of the room. By us increasing the air tightness of the room, if we can get it below, again, now this is in simple terms, but if we could get if there was an air tightness test done on the building and we could get it down below 5 air changes, which would bring it in line with building regulations for new buildings, then we could use different we could use the new build air change rates. So this would go from 1.5 to 0.5. We would also possibly block up the chimney or get rid of the open flue. So this then would go to 0. So straight away, you could possibly shave half of the heat loss from this specific room. So it is important to factor in all the different bits and pieces and see how we can reduce these values. Each room then, again, from a simplistic point of view, would have additions. So thermal bridging being the joint at which two elements meet. So unless this is completely wrapped, it is a source of heat loss through out of a room. In this scenario, there's generally 3 thermal bridging factors. So you'd have 0.15, which would be the standard. You would have 0.08, and then there's also 0.04. But in order to use them lower values, you would need ACDs and signed drawings from the architects and the builders that the thermal bridging has been reduced. So in most cases, you would just take it at 0.15 unless you had the evidence to support it. You would also then possibly add in percentage uplifts for a building being in an exposed location. So when air tightness figures are done, they are done at a specific pressure and at a specific wind speed. So once we go into a more exposed area, so a building up on a hill within a cross breeze area, you would have to allow for possibly more heat loss through air infiltration than is standard. Then you would also possibly have for high ceilings due to stagnation of heat. You could possibly then have in retrofit scenarios, you could have uplifts for pipe losses, etc. So this is the basic method for performing a heat loss calculation: our ventilation losses, our fabric losses, and then any additions. This then will be done for every room in the building. And then you would have your sum total at the end for sizing a heat pump or a boiler or whatever it may be. Once you have then your individual room requirements, then at this stage you can start for sizing emitters. So if you're working out for underfloor heating or radiators or whatever it may be, but this is kind of your starting point. So once this is done for every room following the same method based on the different design criteria for that room, you'll have a full heat loss calculation for a building. The heat loss calculations themselves can become a lot more intricate and detailed, but for the purposes of this overview, if these sort of steps and methods are carried out, it will be fairly accurate. So to summarize really on the heat loss side of things, and to perform a heat loss calculation, the bare minimum that is required is we need to know all the room dimensions of the specific properties. We need to know the window sizes, we need to know floor areas, we need to know ceiling heights, internal walls, external walls, we need to know all about the doors. So you need to know all the different elemental areas of the building. We need to know the design room temperatures. So we need to know what the rooms are. So it's if you had just a plan, but there was no rooms and there was no way of identifying what the rooms are, you could have rooms designed at different temperatures that are incorrect. So like a bedroom being at 18 and a bathroom possibly 22. So you need to know exactly what the room is and what the design temperature is you're trying to get to. We need to know the external design temperature, in Ireland being -3. We need to know the U values of all the different elements. And then we also need to know the air change rates. So once we have these bits of information, we should be able to perform then a detailed heat loss calculation. Next, then we'll just have a very quick overview of DEAP Software. So DEAP Software, or Dwelling Energy Assessment Procedure, is used by BR assessors to calculate the energy performance at carbon dioxide emissions of a home's space heating, the water heating, ventilation, lighting, etc. It is a web-based software, and is used to calculate annual delivered energy consumption, primary energy consumption, and the carbon dioxide emissions. Effectively, what it is that any BER assessment that's done, or a technical assessment, would be on a residential basis, will be done using this software package. Here are just some examples of kind of what some of the screens look like, and what data goes in. It is a fairly significant process, so everything got to do a building will be inputted. So you would have all the elemental areas, window sizes, what orientation they're at. You would have everything got to do. So we see here, you'd have you input data from the floors, so number of floors, how many stories, are the heat loss floors, U values, exposed perimeters, etc. This would be the same for the roofs, walls, rooms, doors, etc. So you would have basically everything from an elemental point of view of a specific building will go in. You would also have all the ventilation details, so infiltration, your structural air tightness, ventilation methods, so is it natural ventilation, is there mechanical ventilation, heat recovery, etc. Mounted different sides, sheltered. You would have the lighting, so how energy efficient is the lighting gone into the building. You would have the proposed or the existing heating system that's been installed, so you would have, is it a heat pump? What are the controls and responsiveness, pumps and fans? Basically everything got to do with the mechanical side of the system. So from pumps to stats, to the amount actuators, everything got to do would go in. Same with the hot water, what type of cylinder is there, what's the control on it, how many circulating pumps, etc. So every bit of detail from the actual building itself will be inputted into one of the various tabs. This being done for both new build and existing buildings. New building, I suppose, is primarily to check that a building will comply with building regulations. Existing buildings then primarily would be from to get an energy rating of the building, whether it be for a sale or letting out a building, or also then if someone was going for a grant, certain targets have to be achieved, uplifts and that. So this software will provide all that. So once all the different information then will be inputted all the way down along the different tabs will fill out, you will get your results. It will tell you then if all the different elements are compliant with the different targets, what your energy rating is going to be. It would have all the different values and results from the building, from a carbon, from an energy, and from possibly on a new build on a renewable basis. For people then on a retrofit scenario, if they're going for a heat pump grant, or if they are getting deep retrofits or shallow retrofits, they would need to know what the HLI, so the heat loss indicator of the building. So this is the software then that will produce that target. So we can see here just this example is 1.1, the target being 2 or 2.3 cost optimal. So you need to be below them. So this is what it'll tell you. Also then on a new build, it will tell you if you're compliant with building regulations. And then also you would have your 3 targets, your energy target, your carbon target, and your renewable target. So the software then will provide you with information to say, yes, the house is compliant, or no, it's not. If it is not, then you can go back and adjust certain parts to see what needs to be done. If insulation in the wall needed to be upgraded from maybe 100 mil slab to 150 mil slab, or if the design flow temperature at a heat pump needed to be reduced from 45 to 40 if possible. So the software will tell you everything you need to know, and it will provide a pathway in order to get a house either from a new build compliant or on a retrofit, how to achieve the targets and what measures can be adjusted in order to reach the targets. So as I say, that's basically just a quick overview of the DEAP software. There's a lot more to it than I suppose what I've shown, but you could get lost going through slides and bits and pieces. For anyone interested in DEAP software, you do not have to be a registered BER assessor in order to use the software. You just have to be a registered assessor to publish a BER. So anyone really within the industry can go on and open an account and use the software, sample it, put in buildings and see how it operates. You can see how it adjusts and how figures go up and down, and it kind of gives a better understanding of how targets are met in both a retrofit and the new build sector. I suppose that's really it on for the overview of heat loss and DEAP software. There's a lot more, I suppose, to it, but just without getting too technical with it, just to give you kind of an overview, that was kind of it. For anyone that is kind of interested in heat loss calculations or what goes into it, I would recommend the CIBSE Heating Design Guide. It gives step-by-step how to do a heat loss calculation, what's involved, what your figures are from design temperatures, from air changes, etc. And also SR50-1 and SR50-4. So that's basically will provide every bit of information needed in order to ensure that heat loss calculations are completed correctly. So I suppose thank you for your time. If anyone has any further questions, you can email the address on the screen. And thanks again.
Perfect. Thanks very much, Barry. We have a couple of questions here. I don't know, would you be willing to answer now or maybe get back to them in some time? But Kieran Rogan asked, where air permeability test results are not available, is there an information source that can be referenced to determine air change rates that should be considered for individual rooms? I don't know, can you see that?
Yeah, so if there is no air permeability test, then you would take the existing building data from the design guide. So you would have your 1.5 or your 3 air changes, depending on the different type of room. So they are the figures you'd use if there was no air permeability. If there is air permeability test and you do achieve values that are up in the new build category, then you can use the new build air change rates. But there's no specific guidance apart from the actual documentation, whether it be a new build or an existing building. So you would use either of them air change rates.
Yeah, very good. Yeah. We have another question here from Shane. He says, are you familiar with any tools for heat loss measurement for the overall building, example HLI, to compare with the theoretical values?
No, I suppose from the heat loss, generally, unless you would have a specific calculator designed yourself or you're going into heat loss thermal modeling, it would generally be done longhand, as we've seen. So actually measuring the rooms, filling out the data into the calculations, working out all the different sources of heat loss from the room, and then measuring it versus the DEAP software HLI. What I will say is the calculated HLI and the theoretical HLI from DEAP, generally there'll always be a certain bit of discrepancy, because the calculated value, as we've seen, we're taking all the individual rooms at different design temperatures, different air change rates, whereas would generally treat a building as a box. So it is slightly different. So your calculated heat loss generally will be a couple of percent above. What SEI require is that your calculated heat loss and your calculated HLI and your DEAP HLI be within 10% of each other. That's generally down to the way they would look at the performance of the heat pumps, that it is accurately sized. If it's above 10%, they reckon the heat pump is possibly oversized. It could be short cycling and lead to higher running costs and so on. But I suppose to answer your question, no, there's not really a specific software that I'd be aware of in order to compare DEAP HLI with your standard HLI.
Perfect. Yeah. So yeah, with that, I'd like to thank Barry and everyone who joined today. It was excellent. Thanks, Barry, very much. Some really good insights there. And for everyone that's here at the moment, we'll have another webinar tomorrow, and I believe it is Benny going to talk about circular economy. So we hope to see you then, and I hope you have a good day.
Thanks, everyone.